Accompanying Section 28, it's called. So you can go there and you can just subscribe to his channel and you can watch them there.
They're on YouTube, you said?
Yeah. He has them posted in Section 28.
And they're recorded, right?
Yep.
Okay, thanks so much.
You're welcome.
I like that. Student discussion during break. I encourage this. All right, Eric. Am I muted? I think I'm okay. I see my voice. There we go. We're gonna.
You're okay.
Thank you. And here we go. Let's continue our Lewis structure discussion. This ion's called the azide ion. Azide ion is in your airbags in your car, creates nitrogen gas when reacted with iron, but we don't need to know that. We just need to do its Lewis structure. Valence electrons, 5 for each nitrogen, 3 of them. Extra electron for being an anion. When we're done, we better have 16. Here's one where we're not going to be able to avoid OO bonds. No charge. This is called ozone. Some of you knew that already. Ozone is an allotrope of oxygen. PNC2 negative. 5 for phosphorus. 5 for nitrogen right above phosphorus on the periodic table. 4 for carbon and 2 extra. That's going to be 16. That doesn't look very much like a plus sign, does it? And same elements, same charge. We don't have to do the numbers again. These are isomers. Now, when they're written this way, you don't even have to figure out the order. You are told the order. P's on one side, C's on the other, N is in the middle. Here we have N. It's got to be attached to another N. Attached to an N. O attached to an O attached to an O. Don't try to get fancy and make triangles. I would not do that to you on a test. You will not be doing Lewis structures for triangles until I tell you to. Okay, now underneath, let's do all 4 go on here. Sure. Let me make it a little smaller. Oh, I don't think I succeeded. Made it bigger. There. All right, and this is going to be P followed by N followed by C, P followed by C followed by N. And in every single example, we've used 4 electrons for the bonds. Oh. Got to come up with 12 more there, 14 more here, -4 for the 2 bonds here. And same for both stories down there. So 12 more. What's my system? I like lone pairs on the outside till the octets are full, and that consumes my 12 that I need. I'm going to consume 12 out of the 14 here. So I have no choice but to go to the middle for the last 2. 12 here on the outside. Keep in mind, these are not final answers, just a system. And same here. Okay. Now, clearly we're not done. Nitrogen in the middle is very far from having a full octet. So what's our process? Take 2 off, put them back on as a second bond. Nitrogen in the middle still has only 6 electrons around it. I don't like the way I drew that. It looked very weird. There. Nitrogen in the middle, 2, 4, 6 electrons, not an octet. Remember what I said about symmetry? Always shoot for symmetry and then evaluate after that. Let's do the same thing on the right we did on the left to make it symmetrical. There you go. That might be done, it might not. We'll see. Same story here, but we only have to, the oxygen in the middle is just 2 electrons short of an octet. Or can I do it? I think I missed a lone pair. I got it. Okay. I'm going to take 2 off of one side, put it in the middle. I got a question for you. Why not take this pair off and then put it here? 1, you didn't solve oxygen's problem. It still has only 6 electrons around it. And 2, the big problem, you created an octet violation on the left side. Shame on you. Don't do that. Okay. What we're doing is taking 2 off here so that the one in the middle can have a share in those 2, whereas it didn't even know they existed till I did this. I believe all of the atoms have octets now. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Good. Here we're going to do the old symmetry thing again. Let's try it on both molecules, see what happens. You're going to be surprised we have very different stories in these last 2. And now it is formal charge time. Okay. This one here, formal charge. Nitrogen owns 2, 4, 5, 6. Periodic table, it owns 5, so that's a minus for that nitrogen. Yeah, let's do a different color. Nitrogen in the middle shares 8, 2, 4, 6, 8. That's like owning 4. It's a plus. The nitrogen on the right looks like the nitrogen on the left. Let's try resonance and see why we're going to put the shadow, sorry, the highlighter on this one. We're going to try the resonance and come up with a structure that's not as good. Okay, my pen's doing that again. And this one won't be as good. I'm going to say this is a weird looking equilibrium arrow. It's going to spend 99.99% of its time on the left and very little time on the right for reasons that I will discuss. The nitrogen on the left is perfectly happy with a 0 formal charge. Why 0? It owns 2, 3, 4, 5. Nitrogen in the middle, kind of like before, it shares 8, it's owning 4. That is a bad-looking cation. Here's where the nitrogen on the right is in dire straits. It owns 2, 4, 6, 7. That's minus 2. Now, intuitively, you're probably thinking minus 2 is twice as bad as minus 1. You are very far off with that statement. Minus 2 is hundreds of times worse than minus 1. If you have a Lewis structure with a minus 2 or a plus 2, it's probably wrong. Okay? That's an extreme amount of charge for one atom. So keep the absolute value of the charges low. You want 1s, not 2s. And 3s, oh my, let's not even talk about 3s. Okay, so I'm just going to cross that thing off. It's just awful. Minus 2 is awful. Okay, now our ozone molecule over here, the oxygen in the middle is plus. The one on the left is 0. It's like a normal oxygen, 2 bonds, 2 lone pairs, all right? Here it owns 1, 2, 3, 4, 5. That's a plus. Here it owns 7, 2, 4, 6, 7. And this one, you can do a Lewis structure that has exactly the same stability. Use your resonance mechanism arrow, move that in towards there, and then dump the lone pair over here, and you'll get something that looks like the first one symmetrically. And we got this. Double bond here now, no charge over there. Now your minus is on the left, plus is in the middle. This one's a 50-50. This spends half of the time like that, half of the time like this. That's why ozone, even though it's a molecule with 2 formal charges, which generally makes things unstable, is not that unstable because it's stabilizing those charges with the resonance. Okay. Down here, phosphorus here is -1, 2, 4, 5, 6. That's -1 because phosphorus on the periodic table owns 5. Nitrogen +1, not terrible. Carbon is terrible. Terrible, terrible, terrible. We might not be able to avoid terrible in this one, though. 2-, it owns 2, 4, 5, 6. Periodic table has an ownership of 2 less. I can get rid of the minus by flowing electrons away from it. Notice when you have a minus and you flow electrons away from it, the minus disappears. When you have a neutral charge and electrons got dumped on it, it goes to -1. So we're going to actually solve the carbon problem and create a new problem on the left, aren't we? So we're going to have a terrible Lewis structure and a very terrible, and then have to evaluate which one's better. By the way, if you do a literature search for a PNC2- ion, you'll probably find only theoretical articles. Yeah, I don't think they've seen this one in the lab for any extended periods of time. Now we have a triple bond here. Next week, we're going to call it a sigma bond and 2 pi bonds. How's that sound? It's minus now because it owns 2, 3, 4, 5, and nitrogen in the middle still plus. I'm having trouble with the pluses in the middle, aren't I? Oh, awful. So how do we evaluate which of those 2 is the least awful? Once again, we're going to use electronegativity. And of course, you've learned them already. 2.5 for carbon and 2.1 for phosphorus. Which one is better able to stabilize a negative charge? The one that brings the negative charge closer to the nucleus, of course. That is carbon with a higher electronegativity. So if you are asked on the test, and you will be, which is the most stable Lewis structure for PNC2-, this is the only one I want to see. I do not want to see the less stable one on the bottom. So you're thinking this is going to be the best one for this one too, and I think you might be wrong. Let's see. The P is a negative. The carbon's neutral. And the nitrogen is -2, I'm pretty sure. 2, 4, 5, 6. No, it's negative. And I stand corrected. I believe this is the best Lewis structure. Because if we resonate in towards the middle, one of the species is going to become a -2. So once again, this is it. Let me slow that down a little bit. Let's just hypothetically resonate. So I'm going to take this lone pair and resonate there. Nitrogen's going to go to 0. That's good, right? But then the phosphorus is going to have an extra electron. That's going to be -2. It used to share 2, and it's going to own them if you dump them on the phosphorus. So that is the best Lewis structure there. And I believe we'll have a nice short segment here. And we'll come back in 5 minutes and do segment 3. And I'll make sure follow the steps. Stop the share. And end. And we'll see you in 5 minutes.